All right, good morning.
Good morning. Good morning.
That was very, Taylor's like, what? It's morning? I know it's unfortunately very, very cold out this morning. I appreciate you guys coming to campus, especially those of you that drove out there in the slick, fun weather. But we're here. Let's talk a little bit about Python. So as we start going through here, we're going to talk about loops a lot. So we're going to work this week on a couple of assignments that are in the Cengage environment. We're also going to look at some assignments and some pieces that are not. So we'll continue our clock discussion about how to build a clock. So the first thing I want to look at is number 3-5. So I'm going to actually open that one up really quickly. Well, as quickly as Cengage will open. I did mention as quickly as Cengage would open. So this is actually a really good example of something we could do in Python that makes life a little easier for us in other sciences. So I'll pick on Taylor because she wants to go into some kind of data sciences. Well, a lot of times it's easy for us to construct a piece of code that will do some of the calculations for us. So here we have a local biologist needs a program to predict population growth. Now, are there other ways to do this? Sure. But let's take a look at this program and see what we need to do. So we have an initial number of organisms, and they're an integer value, a rate of growth, a real number greater than 1 as a float, and the number of hours it takes to achieve this rate as an integer, and the number of hours during which the population grows as an integer. So we have several different pieces that we need to look into here. So make sure my name's in there just so I see who I am. And I'm going to list a variable section just because it makes it a little easier for me to look at these. So the initial number of organisms as an integer. All right, so now organism initial, and I'm going to set that equal to 0. That says it doesn't have a decimal, it's an integer to start with. The rate of growth, so maybe I'll just call that one rate to make life a little easier for me. And I know that that one's going to be a float, so I'm going to 0.0 to indicate that it's a float to Python. The number of hours it takes to achieve this rate, so that one, hours, what could we call that? Number of hours it takes to achieve a rate. Hours per cycle, maybe? And we're going to set that equal to an integer. So in other words, what we're saying is it's going to grow at some rate. So maybe we have this growth rate as 2. So it would double in population. But at what time? And maybe it takes 4 hours for that to double. That gives us a value of how many hours each cycle takes. And then we're going to have the number of hours in which the population grows as an integer. So we could call this hours for growth if you wanted to. You can come up with whatever name you want to do it. And again, I'm going to call that one an integer. So now I can start actually looking at some of my inputs and then get those put in there. So my first one here, now, in reality, Python everything we've just done, Python will ignore in some ways. And we don't necessarily need to do it. But it helps me because it already has those variables in there and I know what I'm working with originally. So, I need to ask a couple of questions. So, I'm going to put in, I'm going to cheat and use their little feature. Oh. Is equal to, and we're going to use an input. In fact, I'm going to move this over just so it makes it easier to do. Enter the, let's see what they use for their verbiage here. Enter the initial number of organisms. Okay. Now, I need one more thing. Notice it says that we want that to be an integer. Well, right now it's a string. And so I have to do my int, and then I go to the end of the line and do the same thing. I need to make myself a little more room here. All right, so it's going to have 2 parentheses. So we convert that automatically to an integer. So our next one then is going to be then our hours per cycle, if I remember right. So, or our rate, either one. So rate equals, and I know that that's going to be a float, so I'm going to go ahead and do the float. And then I'm going to do an input. And then I'm going to cheat just a little bit to save myself some typing. So enter a real number greater than 1. Go all the way over there, you go copy. I'm going to go paste. So my next one then, we have listed as hours for growth, or hours per cycle. We're going to do the hours per cycle. And we're going to say the same thing. That one's going to be an integer. Input. And then I'm going to cheat and once again grab the verbiage right here. I can cheat just a little bit. And in fact, while I'm over here, I'm going to copy this down. As big as I can because it's got a lot of pieces in there. And so our last one then is going to be our hours for growth. And we're going to set that as equal to, that's also going to be an integer. All right. So now I should have my 4 inputs. That gives me some input in here, so I'm going to close that down a little bit. I'm going to run it just to make sure I haven't typed anything really silly. I'm going to put 10, 2, 1. All right, so it took all my inputs, nothing crashed. That's good. So we're kind of on our way here to get there. So we're going to take those inputs then, and now we have to figure out how we can actually use these formulas and make something work for us. So the first thing we're going to have to do is we need to calculate we have to figure out how many cycles we can get. In other words, we're going to put in a number for hours for the growth cycle. So in which case I think I entered 2 or something. And how many hours we're going to have that grow. So we need that to tell us how many of those we can cycle through. Here's where it gets a little tricky. I want it to only give me an integer value, because if we don't get to the end of it, so for example, let's say that we had 6 hours per cycle, and I put in, we're going to allow it to grow 7 hours. It's really only going to get one cycle. It's not going to get the entire cycle done. And I need to come up with a way to do that. Well, if I look at math operations, so sometimes this is really the quickest way. I can take a look here and look at some of these. What do we have here? Floor division, in which case they call it here, where the result is the quotient in which the digits after the decimal point are removed. Okay, that sounds like it could be what we want to look at. So number cycles we could set equal to that hours for growth. So there's how many hours we're going to allow it to grow. And instead of saying a single division, if we put in 2 division lines, and we divide it by our hours per cycle, that should give us a number that is how many cycles this is going to work. So we can test that really quickly. So we can always put in a print, and we're just going to print number of cycles. So I'm going to move this over again, and I'm going to run this. And I'm going to, so I don't really care how many of those there are. And I don't really care about what the growth rate is. But what I do care about is these 2 numbers. So I want to see if it's going to work the way I think it does. So I'm going to say it takes 6 hours for each cycle. And we're going to put 10 hours in. So if I've guessed correctly and written this correctly, it's going to tell me I have 1 cycle. Oh, it does. And so you can test it with other numbers, but what it should do is truncate off anything after the decimal point. So now I know how many cycles there are, so I can finish the rest of my calculations. So now I know each time that this has a cycle number that we're going to run another set of calculations. So there are a lot of ways that we could set this up. This really is a loop that we're going to build. And the number of times it executes that loop is dependent on some of these values here. So in this case, it's going to run this loop once. So we could certainly write this as a while loop, but I think what might be easier is to do this as a for loop. A for loop we can define pretty easily. So, I know it's on the bottom of the screen. For, now, I'm going to just call this pass. We're going to create a new variable, but we're not really going to do a lot with it. So I'll show you here in a second. In range, and that range we're going to call what we used as number of cycles. So we're going to say, as long as this is true, that there is something existing in range, then we're going to create a formula. And that formula then says our initial number, so wherever our initial, so organism initial, and we're going to say is equal to, and we're just going to replace it then, times, where did we put our, what did we call it, the rate. So every time this loops, it's going to multiply whatever we started with, times that rate, and inject it back into this original number. So we could even change that. So maybe that name isn't very self-documenting. So we could go back in and change it to number of organisms might be a better number than organisms original. So in this case, then we need to come back out of that loop and we need to print something that says, you have a population of organisms that is, and then we would put in our, after that, over, organism initial. So again, we probably could pick a better variable name. Units. So what we can do here is we can try this and see what happens and see if this works the way we think it does. Or hopefully it does. Now, I will tell you I probably did something weird. Invalid syntax. What did I do here? Something in my initial. Alright, so that might be a reserved word, so let me try it again. Okay. So sometimes, and I just use pass and it's a reserved word, and I noticed, so when I said that, notice how it color-coded it for me and said, oh, it means something. So that's kind of a hint. So I'm just going to put in a random variable name because we're not actually going to use it for anything. So for x in range, it will do that. So, all right, I'm going to start this over. The total number of organisms. So I'm going to say there's 100. Rate of growth. Let's just double it every cycle. The number of hours to achieve that growth is 1. And the number of hours for growth is 1. And the reason I'm doing this is I want to test this and make sure that that gives me the number that I think it should give me. Oh, it does. 200 units. Perfect. Perfect. But notice that it's still got that .0 after it because I've multiplied times a float, so it's converted it to a float. So I want to convert it back to an integer because I don't have partial. So I can do it right here and put it right around that organism. Run it again. So enter the initial number of organisms, 10,000. Rate of growth, 2. Number of hours, 1. Total hours of growth, 1. And it should tell me that I have double that. So you can try this with all different kinds of numbers. So we could try it again. And so we have 1,000 or 10,000 units. The growth rate, we could say it's very, very high growth rate, and it's going to grow even faster. Maybe it grows every half an hour. And the number of hours, so we're going to give it 24 hours to grow at that rate. Oh, I hit the wrong button. All right, never mind. Let me try that again, because now I made it angry. All right, so 10,000. The growth rate of 2. The number of hours is 0.5. Sorry, I got the wrong one in there. Now, why is it going to do that? So I tried to say it's 0.5. Well, if I look at my code, what I take in for that rate of growth, so the rate here, but when we multiply it and we're working with an integer, sometimes it doesn't always work the way we would hope it would. So, integer of 0 with a base 10, so it can't convert that to an integer is what it looks like. So, let's try it again. And so we'll try it at 2 and 1 hour, 24 hours. Holy cow. So that's how fast some of the viruses and bacteria and things are going to grow. So this is kind of a really quick tool. Now, once I get this done, I'm going to check it, and let's see if I'm anywhere close to what Cengage wants. Oh, looky. Hey, that's pretty good. But I noticed that there's some things I would clean up. So one of the things I notice is I'm not very consistent about making sure I have a space here And I know that for mine, so chunk, chunk. So little things like that, I would probably, if I were turning this in as a standalone assignment, I would change this, because while this looked like a great value to start with, organism initial, once we start using it to calculate how many there are now, there's probably a better value I could use. Because what I want is my code to self-document. So I want my variable names. Because Python doesn't care. If I did this as A, and this is B, and C, D, Python doesn't care. But it makes it easier for us to understand those. So 3.5 should give you something similar to this. Now, I could do the same thing with a while loop. So instead of doing a for loop, I could do this as a while loop. So while, what do we have there? So number cycles is greater than 1. And then I would just have to also then have the advantage of that for loop. It takes care of that addition or subtraction. And then I could have to say it's like number cycles equals number cycles minus 1. So that if we started with 24, it would loop through here until it got less than 1. And so you can try those out. There's a lot of different ways to do the same program. So you can use a while loop. You can use the for loop. The for loop has that advantage of not having to have this sentinel value altering step in there. It does it automatically for you. So, and you can actually do those ranges where it goes down or up or anything else. So in this case, you could do it that way. There's thousands of different ways you could do it and achieve the same number of loops. But sometimes you may want to put a counter in to make sure that you're doing it the right number of loops. That starting with 0 will sometimes screw us up, so we do one more or one less loop than we intended to. Alright, so that's 3.5. Let's take a look really quickly at 3.6. Again, as quickly as Cengage will let us do that. Go. Alright, so this one says, mathematician Gottfried Leibniz developed the following method to approximate the value of pi. So pi divided by 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus, and on and on and on and on. So in this case, we're going to have to figure out a couple of things. I'm going to have to come up with what variables I'm going to have. And let's see what enter the number of iterations, and the approximate value of pi is 3.3 whatever. Alright. So what we're trying to get is how close to pi we can get, and using a mathematical formula that we're given up here. Alright. So we have to do a little bit of algebra here. So that's kind of the scary part. So what I'm going to do is leave to the last this piece here. So what I would like to do is transform this equation where pi is all by itself. And to do that, if I'm dividing by 4, I'm going to multiply this whole side by 4. So I'm going to get a value, and then I'm going to multiply it times 4. And I'd like to do it at the end, just to start with. So first thing I have to do is I'm going to actually just call this iterations, since our value up here says how many times are we going to iterate that. So I'm going to say iterations is equal to 0. So I have one variable in there. So I'm also going to start out with a couple of other variables, because I know that over here I'm going to have a numerator and I'm going to have a denominator. So I'm just going to call them that, numerator. Now, here's where I'm going to change my one statement, because all the way through there, the numerator is always 1. So I'm just going to set it to 1 right here. So my denominator, well, at the very first one we run, 1 over 1 really is 1. So it's got a denominator of 1. So I'm going to actually start this one also at 1, just to make my life a little easier. So I have how many times it's going to run, my denominator, my numerator, my denominator, and then I want this value over here. Now, I said I'm going to cheat, and I'm going to multiply it times 4 at the end, but I think that I might want to call that pi 4 maybe. Something to identify that it's not really pi yet, but we're working on it, and it's divided by 4. So pi divided by 4, pi whatever, temporary pi, whatever you want to call it. And I'm going to set that equal to 0. So we've got that zeroed out. Well, I'm going to have to ask my user how many iterations they want. So iterations is equal to input. And again, I could go steal their text, but I'm going to really quickly. Please enter the number of iterations and that should work. Now, there's a, well, let me hit it. All right. So now, I'm going to have to create a loop. So that loop is going to be how many times we have those iterations. So we can do it in a lot of different ways. So we could do a while loop. So we could do a while iterations is greater than 1. And then we make sure that each time we loop this, we have iteration equals iteration minus 1. So that it will loop through a set of loops. We could do it with a for loop. You could do, there's tons of different ways you can do it. All right. So the next piece that we need is we need to figure out what we're actually going to do with those numbers. So each time we come through here, so we're going to have to loop however many pieces there are here. So this is 1 iteration, this is 2 iterations, this is 3 iterations, that's 4 iterations. So each time we do this loop, we know that that denominator plus 2, right? Now, I probably need to look at my math operation first. So the first thing I'm going to do is I'm going to take the numerator divided by the denominator. And so I have to do that. So what did I call my group up there? Pi 4? And because I'm going to replace its value every time, pi 4 equals pi 4. And I'm going to add numerator divided by denominator. Okay. So that would be great if all of these were pluses. But crap, they alternate plus and minus. Yeah, great. So I have to come up with some way that I can flip it every loop that it goes from positive to minus. So here I said I'm going to just add it to it, but let me show you a kind of a cheating way to do this. So notice it's a minus 1 divided by 3, minus 1 divided by 7. So every other time that numerator changes its sign. Well, so if I just did numerator, and I'm going to say it's equal to numerator, but I take it times negative 1. So the first time it comes through, it's going to be a 1. So once it comes through here, so our numerator is 1 divided by the denominator. This time, then it flips it to a negative 1. My denominator increases by 2, and we come back up to the top of the loop. Now, one thing I will do here is I'm going to do this, and I'm going to put this below it, just because I want to have that as my last statement. So, while iterations greater than 1, pi 4 equals pi 4 plus the numerator divided by the denominator. Okay, that makes sense. My numerator equals my numerator times negative 1. So once I've calculated what this value is here, once I've calculated that, then I flip my numerator for the next round. So the next time this loops, it's ready to use. And I increase my denominator by 2. So it's 1 the first time. Now it becomes negative 1 for the numerator, and 1 plus 2 is 3 for that. And then I take out 1 for my iteration. Does that make sense? So the end of my loop then, so after this finishes, then maybe I just come up with a pi, and I spelled it that way on purpose so it isn't a reserved word, equals then pi 4 times 4. And again, that's that algebra of we have all of this side calculated, and we want to set pi equal to, or just have a blank over there, so it's the only thing on that side. So we multiply both sides by 4. And so then we could output the approximate value of pi is, we could do that. So let's run this. I typed a lot, and we know that when I'm talking and typing, bad things kind of happen. So let's see what happens when we run this. Please enter the number of iterations. So let's do 10. And somewhere I have a problem in there. Name iterations. Oh. Iterations, iterations, iterations. Okay. Try that again. Type error greater than not supported. Oh, so. Notice what we did. I took an input and I tried to perform math operations on it, but it's a string. So the other piece I need to do is do this integer. So again, anytime I take in an input, it comes in just as a string. So let's try one more time. Line 15. And once again, I apparently can't type my own variables while I'm sitting there. Delete. So that is iterations equals iterations minus 1. We'll use a little cheat sheet there. All right. All right, try it again. 10. The approximate value of pi is 3.25. Is that close to pi? What's the value of pi that we think of? 3.14? All right, so let's try that again. But this time let's put in, see how much we can bog it down. Let's put in 10,000. Oh, and so the more iterations of that, the closer to what we consider pi is in there. And we can actually do some, so after we look at this to test it, we can actually look at what pi looks like in this system. So you could do it to 10,000 iterations. So you could actually then add import math, and then we could actually print math.pi, and so you could compare the two of them. So I didn't want to tab that out, but it's getting closer, so maybe run it again and we go to 100,000 iterations. So the more we run this, the closer those two numbers get. And so you could certainly check those. You could even subtract them and say, this is our estimate, this is what we know pi is at that value. So, and I'm not sure what value will kill it. Let's see here. If I go, that's 100,000, that's 1,000,000, 10 million. Try that. Didn't like that. So 1,000,000 iterations, so it's cycled our loop 1,000,000 times in there. Isn't that kind of crazy that it can do it that fast? So what would be really crazy is if you looked at the numbers for what the denominator and those different pieces are, you could certainly look at them. So I don't think it will do 10 million. Oh, it did. So kind of interesting to see how fast even these computers can run a single thread like that. So you could actually do a count in there. If you wanted to, what might be interesting, so in this loop, after we do our calculation, what if I just did a print so pi 4 times 4, so it's going to give us the same value as down here, but we can actually see it count off when we do them that way. So just kind of an interesting way to do it. So 10,000. And then it's going to take it a while now, because if I scroll all the way up, you can scroll all the way down, and what actually takes a lot of time is the printing to the screen. So it's not done yet calculating. It's just because the printing to the screen is so much slower than the calculations in its internally. So you can see where we started at, and as we got closer and closer and closer and closer to what the value of pi would be. So, all right, I'll break that real quick. So let's go in and check it. I'm going to first remove this at the bottom, or at least error it out. All right. And let's see, that will just add necessary headache. So let's go see if this comes up with similar to the results. So one of the problems with these checks is it puts in input, puts out output, and in this case it says, oh, there's something wrong with our output. Okay, hold on a minute. Let's see what's wrong with our output. Test for 1 iteration. And it should give us 4. Test for 5, test for 9,999. All right, so it's saying we have something wrong with it. So let's take a look. See if we can restart it here. 1. The approximate value of pi is 0. Okay, so maybe we do have something wrong in the way that this calculates our values. So we'll have to do a little troubleshooting to see why we come up with a 0 and it's saying we should come up with a different value. So we can also test for 5 iterations. It'll tell us what it should be. So for 5, this is what we should get. So I'm going to run it again with 5. And those two numbers are vastly, vastly different. So why is that? Why are we getting that? So I need to think about how this is running. So while iterations greater than 1, this is going to run. So pi 4 equals pi 4 plus the numerator divided by the denominator. So when pi is 1, so did I start this right? So iterations are 0 to start with, but we're going to change it to 1. So while iterations are greater than 1, oh, so what if I really need to say equal to or greater than 1? Let's see if that makes a difference. Nope. Put it in the right order. Greater than equal. Now we'll run it. Number of iterations, 1. Oh. Because we had it listed only as greater than 1, when we put in 1, it didn't ever run. And so we were one cycle off from what the output really should have been. And that's that idea of we can start from 0. So if we do a 5, which is our other test case, 3.3928. So now if I ran my checks, I would hope and look at that. We go from none of them working to all of them working. And that's a pretty subtle change in the way that our loop runs. So, a lot of different ways we could do this. So maybe the better way to have done this, to make sure that my iterations are correct, maybe I should have done this as a for loop. So for, let's just call it count, and then we could actually use it if we want to pull it in there. In range iteration. Alright. So now, if I run this, let's make sure it works again. For count. I didn't have a space there. Alright. So if I do 1, it should give me 4. So this is the same program, but instead of using a while loop, we actually used a for loop. It does the same thing. So just another way we can do that. Here I've just condensed them down so you can see that they're in this block. So the advantage to doing this, or one advantage, is I've got this variable, and if I wanted to print count, so run, and it will show me, hey, 0 through 9, because that's what we counted to 10, right? So, or, you could print that count at the end to make sure that it really did, over that number of variations, it really did come up with it. So, just a couple of different ways and some things to be aware of on those loops. And again, it's that making sure that Des got it. Greater than 0, greater than 1. So, we could have changed it a lot of different ways. We could have changed it instead of greater than or equal to 0. We could have said greater than 0, and as soon as it hit -1, it would have tripped. So, there are thousands and thousands of different ways we can do the same kind of problem. Alright, so I would hit submit if I had that one ready to go. And we'll look at, we should be able to look at 3.8 really quickly. start thing. Ah. So, this will take us back to pre-algebra, algebra. What we're looking for is something called the greatest common divisor of two integers. Ooh. So, my child would be excited if I did this one for her, so she wouldn't have to actually calculate these by hand right now. So, the greatest common divisor of two integers, a and b, is the largest number that can be divided evenly into both of them. All right, so this one's again another math problem. So the first thing we're going to have to do is we need two integers, right? So I may just call them 1 and 2, or first and second, or so integer 1. So maybe we just do, I don't want to use integer because I think it's going to be a keyword, so maybe I just do first, and I'm going to set that equal to 0, second equal to 0. And you can use any variable that seems to make sense. I need to get those as an input, so I'm going to say first equals input of enter. Now, one thing we can do to make life easier for us is we can actually force you to put in the numbers in a specific order. Now, we'll learn how to reorder them and do different things, but I'm going to say if we force the user to put them in this way, it's going to make our life just a little easier for now. Enter the larger number. Space, colon, space, and since I said larger, let's just make it consistent in my, alright, so, notice what I didn't do, and I almost forgot again, I need to convert those to integers. So, now, I need to figure out a couple of things. So, let's see what it says. Compute the remainder of dividing the larger number by the smaller number. Okay, we can do that. Replace the larger number with the smaller number and the smaller number with the remainder. Okay, so you're flipping numbers. So maybe we need to pop up like a Word box or something and try to show what we're doing here. So blank document. So if we had two numbers, and let's say we put in 100 and we put in 50. So what it's telling us to do is compute the remainder of dividing the larger number by the smaller number. Well, actually, let's do this. Let's do 30. So we get a remainder. So what it's saying is divide 100 by 30. Okay. And replace the larger number with the smaller number. So now they've flipped positions, and so now we're going to have first is now 30. Second is going to be the remainder of that. So 100 divided by 30 is 3 something, so it's got a remainder of 10. So then it becomes 30 and 10. We do the same thing, 30 divided by 10, and then we flip those around, so 10 and 0, whatever we had. So it'll sit there and flip-flop these numbers. So repeat this process until the smaller number is 0. The larger number at this point is the greatest common divisor of A and B. Alright, so that sounds horrible, but I think it's not going to be as bad as what we're thinking. It's hard to visualize. Alright, so I'm going to put in my calculations phase. Or my calculate whatever I'm typing there. Alright, so first thing we've got to do is we're going to say, so we need to come up with a remainder. So remainder equals, and we want to divide the larger by the, so it's going to be second, but we want the remainder, and we're going to divide it by the first, right? But we want the remainder of that calculation. So, all right, hang on. I'm going to go back up here because this is kind of handy to have. We have one called the modulus. Divides the left-hand operated by the right-hand operated and returns only the remainder. So b divided by a, and it gives us the remainder. Well, so let's see if that returns what we want it to. So, all right, so I'm going to print remainder. All right, so I'm going to first run this and just see what happens. So I'm going to put in 30, 100, and it gives me a remainder. Well, that's pretty cool. Okay, so that seems to work. Got it. So my next step then, it says replace the larger number with the smaller number and the smaller number with the remainder. Okay, so replace the larger number with the smaller number. So second, which was our larger, and maybe now I should have done larger, smaller now that I'm looking at this. We're going to assign it the value that's in first. Well, that's easy enough to do. Then it says, and the smaller number, so first is then equal to our remainder. Okay. All right. So I'm going to put in a couple more print statements just to see if making sure. So I'm going to print first, second. Because I want to print these after we run this just to see what happens. So I'm going to put in the same numbers, 30, 100, and it prints the remainder. Okay, and we put that into first, yep, and 30 goes into second. So it's doing what we want it to do. Now we have to figure out how we're going to put this into a loop. So remember, it says you're going to do this over and over again until the smaller number is 0. Ooh, okay. So let's see if we can come up with one. So while, and the number we're going to look at here, while, so remember, first is our smallest one until the smaller number is 0. While first greater than 0. All right, and then we can tuck all of these in there. So those should iterate enough times, hopefully, and then we could come up with something, print the GCD is, and then it should be our second number, what used to be our larger one. So again, I probably would have used largest and smallest had I really thought that out. So let's see what happens if I run this. So chunk, and let's put in a number. Smaller number is 25, large number is 100. The GCD is 25. Now, I'm going to take out those print statements here in a second, but I like them in there when I'm trying this out. So let's do 100, and let's do our 30 again. The GCD is 10. Yeah. Well, this could be kind of handy. 187.19. The greatest common denominator is 2. And it went through all the iterations to show you how you did that. So I think this works, so I'm going to comment those out because those were a good test statement. But this sounded really hard, but the program itself wasn't that bad. So I would look at it and let's see if we get the same comments. Come on. Come on, Cengage, you can do it. Yeah. You could have also done this as a for loop if you wanted to. I like while loops. It's just one of the first things I learned how to do, so that's kind of me. All right, Cengage, sometime in the next century. So why did it give us one? Incomplete. So, not really sure why it did that. Not sure what it was doing there. I'm going to try. So the numbers it tested, 162 and 8571, but it almost looks like 162, 8571. Interesting. 85 and 172, or 162 and 8571. So why is it doing? Oh, hang on. I have an extra print statement, and that may be why it's doing something. Okay. Print remainder. I don't want any of that. So let me try it again. Break. It made it angry. It made it very angry. Let me go out of there. See if it will come back. If it lost all my code, I'm going to be cranky. It shouldn't have. Oh. Oh, it did. It took all my code out. Oh. Alright then. That's not good. Well. Alrighty then. We'll stop there. I think it's actually those print statements that are causing the issue. So I will recreate it real quickly and see if I can force it to give us the correct answer. Alright. We'll finish up this chapter then on Thursday. And one more week then until spring break. Are we excited about break?
Yep.
I was like, yeah, whatever.